continue to make discoveries. We will continue to move forward as much as we can, as safely as we can.
NASA's lunar sensors are still gathering amazing information about our nearest cosmic neighbor in 2024. What if these devices were able to pick up on something unusual? Rhythmic signals that might be coming from the moon's interior. One day, patterns that could challenge our knowledge of what lies under the lunar surface may be discovered by AI analysis of lunar seismic data. Is the core of the moon more active than we've long thought? The interior of our satellites is starting to take on a more dynamic appearance, thanks to new research methods and sophisticated analytics. The moon has been regarded as geologically dead by the majority of scientists for decades. All those billions of years ago, its core cooled and solidified. However, new research indicates that the moon's innards may be more intricate than previously believed. Our understanding of the lunar surface has been revolutionized by NASA's Lunar Reconnaissance Orbiter. In the meantime, new information about what might be occurring below is being revealed by seismic data from both contemporary equipment and reanalyzed Apollo-era records. According to Dr. Katherine Johnson, a planetary scientist who specializes in lunar geophysics at the University of British Columbia, the most recent analytical tools, including machine learning algorithms, are allowing us to detect subtle patterns in astronomical data that might have been missed by conventional methods. Seismologists are fascinated by the moon's surprising seismic characteristics, even though there is currently no conclusive evidence of active pulsing in the lunar core. Apollo-era seismometers recorded moonquakes that ringed for a lot longer than usual, indicating that there may be something peculiar about the moon's internal structure. Scientists are excited to use AI analysis methods on both newly collected and stored lunar data as they develop. Could these advanced techniques uncover patterns in the moon's seismic activity that had not been noticed before? Researchers are enthused about the possibilities. The equipment on NASA's Lunar Reconnaissance Orbiter, which was first built to scan the moon's surface, are sensitive enough to pick up minute vibrations. Researchers have been looking at this data in recent months and have found abnormalities that are difficult to explain by recognized lunar occurrences. At what looked to be regular intervals, the signals were steady but dim. Initially, these patterns were eliminated as background noise using conventional seismic analysis techniques. Such modest rhythmic fluctuations were not detected by standard algorithms that were calibrated to detect abrupt events such as moonquakes or meteorite strikes. The signals just didn't match the lunar seismic activity profile that was predicted. What if sophisticated AI could identify patterns that are missed by human analysts? Today's scholars are examining just this. Rhythms that conventional analysis misses may be discovered using contemporary machine learning algorithms that are built to identify minute patterns in intricate datasets. These advanced devices could be able to detect signals that seem to come from deep into the lunar structure. The regularity of these possible patterns would be their most interesting feature. They might indicate a systematic procedure instead of random occurrences if they happened at regular intervals. Cross-validation of data from several lunar missions could assist scientists ascertain whether comparable patterns exist across various detection systems, even though they would initially view instrument anomalies as the most plausible explanation. Dr. Mark Robinson, principal investigator for the Lunar Reconnaissance Orbiter camera, says we must be open to unexpected findings when studying lunar data that don't fit our present models. We are always surprised by the moon, and new analytical methods may show us things we haven't noticed. Hit subscribe now and enable notifications if you're interested in discoveries where state-of-the-art technology uncovers cosmic secrets that are hidden in plain sight. Every week, we discuss the relationship between technology and space exploration. The mystery of the cosmos grows. However, what could scientists learn if they contrasted data from other celestial bodies with possible lunar signals? The ramifications might be astounding. These days, machine learning systems are very good at identifying patterns that human analysts could completely overlook. Large volumes of data can be processed concurrently by these AI systems, which can identify correlations between several variables that are not visible by conventional analysis. By removing the noise that usually overwhelms weak signals, these systems may be able to detect faint rhythmic patterns in lunar seismic data. Machine learning techniques may look at the full spectrum at once, searching for statistical anomalies that diverge from random distributions, in contrast to traditional analysis. Knechts uses analysis of the spectrum, then the metadata on machine learning techniques may look at the full spectrum analysis that concentrates on particular frequency bands. According to Dr. Renee Weber, a planetary scientist who specializes in lunar seismology at NASA's Marshall Space Flight Center, the difficulty with lunar seismic data has always been distinguishing real signals from the noise. Our conventional filters may not be suitable for the moon's distinct structure because they are based on Earth geology. Instead of beginning with a model of expected lunar activity, this technique is groundbreaking because it can stay agnostic about what should be there. Simple statistical patterns could be found and presented for scientific understanding by sophisticated computers. Researchers would first put the results through a thorough statistical validation process. If the investigation were to reveal consistent rhythmic signals, they would have to ascertain whether the pattern is greater than what could happen by pure chance. In order to verify that the pattern is present across various samples, this would entail methods such as cross-validation, which divides the data into subgroups. It would take several lines of evidence to separate an actual lunar occurrence from instrument artifacts. Potential factors such as orbital changes, electronic interference, or thermal expansion of equipment would need to be ruled out by scientists, comparing data from other missions and instrument types to see if the same pattern emerges on its own could be a potent strategy. Dr. Weber says the scientific method requires skepticism when we discover something unexpected. However, things become quite fascinating if a signal remains consistent across several instruments and processing techniques. What if there is more to these possible lunar rhythms than meets the eye of science? If verified, they might cast doubt on our basic assumptions about purportedly dead celestial bodies in our solar system. We have categorized worlds as either geologically active or inactive for many years. What if there are more intricate internal processes in reality that we aren't currently aware of? Is it possible that planets and moons that we assumed were inert actually had delicate rhythmic processes going on deep inside of them? Consequences for the entire solar system. The ramifications of finding rhythmic activity in the moon's interior would go well beyond our nearest neighbor. The discovery would compel us to reevaluate the way we categorize the planets in our solar system. Astronomers have classified planets and moons into basic groups for many years, either dead or geologically active. Mercury has died. Mars is largely dormant. Io, the moon of Jupiter, is quite active. What if, however, reality is more nuanced? What if our present tools and analysis techniques have failed to identify a range of internal activity? Similar patterns on worlds we've long thought of as frozen might be revealed by the same technology that could detect minor changes in the lunar core. Similar rhythmic mechanisms may be present in Mercury's very huge metallic core. Even the frozen moons of certain outer solar systems may exhibit significant interior dynamics that are not predicted by present models. The idea that these minute core motions might point to energy sources we've missed is perhaps the most intriguing. On Earth, our protective magnetic field is produced by the mechanics of our core. The moon's possible cycles might indicate processes that could affect the long-term evolution of comparable bodies, but they would be far too faint to produce a noticeable magnetic field today. Future mission planetary scientists are already investigating the potential integration of sophisticated sensors and artificial intelligence, AI-powered analysis, into future spacecraft. In the upcoming years, both NASA and the European Space Agency intend to place additional seismic instruments on the moon. These missions could offer conclusive information on any possible rhythmic occurrences if they are outfitted with the appropriate detecting capability. Knowing the interior dynamics of a celestial body offers applications for further research that go beyond simple scientific interest. From where to land to where to erect permanent structures, risk assessment is a part of every mission planning process. Over time, surface impacts that are faint but detectable may occur in regions above deep interior activity. Even slight periodic movements could affect the structural integrity of habitats intended to persist for decades. This information would be necessary for engineers planning the first permanent moon base to choose the best sites and modify their building techniques. Additionally, a better understanding of the moon's internal structure might help with resource utilization. The geological history of a planet, including any current internal processes that might propel material circulation, even if slowly, is closely linked to the distribution of important elements. Rethinking the science of the moon. Our understanding of the moon's interior is starting to shift as a result of advanced analysis tools. A number of long-held beliefs about our celestial neighbor would be called into question if rhythmic signals were found emanating from deep inside the lunar core. The interior thermodynamics of the moon have long been thought to be rather straightforward. The original heat of a cooling organism is gradually being lost. Potential core activity, however, would point to more intricate mechanisms at play. Even a tiny amount of movement within a partially molten outer core might sustain temperatures for far longer than previously thought, according to computer models. Our knowledge of the moon's age and interior makeup would be significantly impacted by this. According to current theories, iron makes up the majority of the lunar core, with smaller amounts of metals like sulfur. There would be enough lighter elements to lower the melting point and preserve partial fluidity for billions of years if rhythmic activity were verified. What this might reveal about possible energy sources inside the moon is arguably the most intriguing. Although radioactive decay plays a role in Earth's core dynamics, the moon's smaller size should have accelerated cooling and solidification. Higher quantities of heat-producing radioactive elements or some other mechanism sustaining temperature differentials would be suggested by persistent activity. This would change the way geologists understand the moon's long-term evolution. It may be necessary to re-examine features that were previously exclusively ascribed to ancient processes. A dynamic core's slight but enduring influence may be able to explain lunar crustal thickness and composition oddities that have baffled scientists for decades. Such a finding would have a significant impact on the objectives and designs of space organizations preparing for future lunar missions. In order to better study these phenomena, NASA's Artemis mission and other multinational lunar initiatives would probably modify their research payloads. Efforts to use resources would also be impacted. Determining the locations of valuable material resources requires an understanding of internal lunar dynamics. Resources that wouldn't exist on a completely dead globe would have been created if heat flow from a partially active core had concentrated some elements in predictable patterns. Other celestial bodies are already undergoing adaptations of the analytical methods that could uncover such lunar patterns. Analogous methods may reveal hitherto unidentified trends in data from Mars, Mercury, and the ice moons of the outer planets. What we discover about possible moon dynamics may contribute to our comprehension of delicate solar system processes. Procedures for verification. Extraordinary proof is needed to support extraordinary claims. Before being accepted, any possible finding of periodic lunar core activity would have to pass stringent scientific scrutiny. Peer review would be the first step in the verification process. To determine whether they arrive at comparable conclusions, several independent teams would need to examine the same data using various approaches. This method lessens the chance that programming mistakes or algorithmic biases would affect the outcomes. Another important verification approach is historical data. The only direct observations of lunar interior activity that we currently have were made during the 1969 to 1977 Apollo seismic tests. When applied to this archival data, new research tools may uncover subtle patterns that were missed by previous approaches. There would be several cross-checks and contemporary verification processes. First, verifying the signal across various sensor kinds and missions will help rule out instrument artifacts. Second, using correlation analysis to rule out outside factors like solar activity or Earth's gravitational pull. Third, creating physical models that are compatible with known lunar characteristics and can explain the patterns that have been observed. More and more astronomers are discovering that sophisticated computer analysis can highlight hidden phenomena in the data that is already available. Subtle patterns in exoplanet transit data that had been overlooked for years were recently discovered using machine learning techniques. Density wave patterns indicating hitherto unidentified lunar tilts were discovered using similar techniques on Saturn's rings. These examples demonstrate how fresh analytical techniques can glean more information from pre-existing findings. When we contrast possible lunar rhythmic signals with comparable occurrences throughout our solar system, however, the most unexpected possibility becomes apparent: relationships between planets. Cutting-edge computer analysis of the available planetary data reveals fascinating parallels between celestial bodies that were previously believed to be very distinct. The gravitational field. Measurements from Jupiter's moon Europa show faint rhythmic fluctuations when researchers use the same pattern identification methods on the data. The interaction between solid and liquid layers deep within these bodies may be the shared underlying cause of these patterns, despite their differing frequency and amplitude from any possible moon signals. The possible link to Earth's core processes is arguably the most intriguing. At erratic periods over hundreds of thousands of years, the magnetic field of our planet reverses. These reversals could reveal universal principles of how planetary cores change and behave throughout time, as they may share underlying mathematical patterns with the delicate rhythms that may be present in smaller bodies like the moon. This has important implications for our understanding of planetary evolution. We might find a range of interior dynamics that scale with size, composition, and age, rather than viewing celestial bodies as either active or dead. While smaller rocky bodies may have minor rhythmic activity that had not yet been discovered, the greatest gas giants continue to exhibit evident energetic core processes. These events may be explained by a few similar factors in several worlds. Regardless of a body's overall size, comparable patterns may be produced by the interplay of rotation, internal heat distribution, and the slow crystallization of inner cores. According to computational models, very slow fluid movements in a partially molten layer may produce recurring pressure changes that are noticeable at the surface, even in smaller worlds like the moon. The horizon of research. This field's future depends on creating increasingly complex analysis methods to glean the most information from sparse data. In order to handle the very different conditions of other worlds, machine learning algorithms that were trained on Earth's seismic patterns are being modified. These algorithms may be able to identify patterns that conventional analysis would completely overlook. A number of future lunar missions are integrating sensors that may directly study these events. Plans for new seismometers that are significantly more sensitive than the devices used during the Apollo period are part of NASA's Commercial Lunar Payload Services program. An array of sensors created especially to pick up faint long-period signals from deep beneath the moon could be deployed by the European Space Agency's Lunar Pathfinder mission. Another area of study in this field is predictive modeling. Researchers can produce testable hypotheses about what signals should be present if specific interior processes are taking place by fusing fluid dynamic simulations with our understanding of the composition of the moon. These models develop a theoretical foundation that can be verified or disproved by subsequent missions. The possibility of mapping the lunar interior in hitherto unheard-of detail, utilizing any confirmed rhythmic signals, is arguably the most thrilling. Lunar scientists may be able to use these regular pulses as a natural sonar system, exposing the composition of the deep interior and the exact borders between various layers, just how geologists use seismic waves to picture the underlying structure of Earth. Our understanding of our nearest celestial friend would be drastically altered if there were evidence of faint rhythmic movement within the moon. Though much more subdued than Earth's spectacular plate tectonics or volcanic eruptions, what appeared to be a cold, dead rock might turn out to be a world with continuous interior activity. This immediately relates to our initial query. Could something amazing be detected beneath the moon's apparently arid surface by NASA's lunar sensors? The solution is still pending additional missions and more thorough investigation. There is little doubt that as technology develops, so does our knowledge of the moon. With several notable exceptions, modern science continues to classify the moon as mostly inactive. We are aware that it has a partially molten outer core, undergoes moonquakes, and has signs of very recent volcanic activity in certain areas. The existence of rhythmic core mechanisms is still up for debate, an intriguing area for further research. We're learning that many cosmic secrets have been concealed in plain sight inside data that we already have as computing tools continue to progress. Our cosmos is shaped by patterns and processes that frequently function on scales that are too big, too small, or too subtle for human perception. The universe is more active, linked, and exciting than we could have ever dreamed, thanks to advanced analysis techniques that are becoming our expanded senses. You won't want to miss our future video on how comparable analytical methods are uncovering hidden patterns in Mars rover data if you enjoyed this investigation of possible lunar findings. To ensure you don't miss it, subscribe and click the notification bell.